Okay, so we're starting into linear algebra, and we're going to do an introduction to systems of equations. The first thing we need to do is establish notation for a linear equation. So what we're going to do here is we're going to create a sequence. So we're going to let the sequence of AKs, not ANs. So it'll be a sequence of AKs from k equals 1 to infinity, be a subset of the real numbers. So this is a sequence of reals, and we're going to let b be an element of the real numbers, such that I make a sum from I equals 1 to n of ai xi is equal to b. Okay, so basically we're adding up a bunch of constants in front of variables, and that's going to get me to some constant. So we say that this is a linear equation of n variables. Okay, so this sequence up here, we call these the coefficients. This is the constant term, so these are coefficients. This is a constant term. The first coefficient, a sub 1, is called the leading coefficient. And the first variable, x sub 1, is the leading variable. Okay, so we need the idea of a solution to a linear equation. These are sequences of values for the variable. So we're going to let x sub k from n equals 1 to infinity be a subset, not infinity. Should be k equals 1 to n. Be a subset of the reals, such that this linear equation is true. If that's the case, then we call this sequence a solution to the linear equation. Okay, so let's give this an example. Let's say x1 plus 2x2 is equal to 4. So we're going to solve this. So let x1 be some parameter t. This is implying that t plus 2x2 is equal to 4, which implies that 2x2 is equal to 4 minus t, which implies that x2 is equal to 2 minus 1/2 t. Okay, so this set of x1, x2 values, right, the ordered pair, where x1 is equal to t and x2 is equal to 2 minus 1/2 t for all t which are elements of the reals, is the solution set for this equation, because whatever element of this set that I pick, it makes this equation true. Okay, so now I want a system of linear equations. So Now, instead of having a sequence of coefficients, I have to have an array of them. So A is going to be Aij, where I is going to be 1 through m, and j is going to be 1 through n. And that's going to be a subset of the real numbers. And then we're going to have a sequence of bi's, where I is equal to 1 through m. So there's m different I values. So if I build a sequence of serieses, so I have a sequence of serieses where j equals 1 to n, aij x sub j is equal to bi, and that sequence is indexed I equals 1 to m. So we have basically a sequence of m linear equations that have n variables. Okay, so a solution to this is again a sequence x sub k from k equals 1 to n, where this sequence solves all m equations in the system. Okay, so if the system has a solution, we call it consistent. If the system lacks a solution, we call it inconsistent. So having one or more solutions makes it consistent, and if it lacks a solution, we call it inconsistent. This brings us to a theorem. If a system has n variables, one of the following must be true. Either 1, or I guess A, the system has exactly one solution. B, it has infinitely many solutions. Or C, it has no solution. So we're not going to go in depth in this. In algebra, you saw that this had to be the case for a system with 2 equations. If this is a limiting factor for 2 equations, it'll work for any system of m equations where 2 or more exist. Okay, so we're going to get into something that's called row echelon form. Row echelon form of a system of equations. So we have to have a system of equations, j equals 1 to n of aij x sub j is equal to bi. I is running from 1 to m. So this is a system of equations where aij is equal to 0 for all I greater than j. So for all I greater than j. So if I is bigger than j, then the row number is bigger than the column number. Then we're going to get a 0 value. Okay, so if this is the case, then we say we are in row echelon form. Okay, so let's give an example of this. If I have the following system of equations, x1 minus 2x2 plus 3x3 is equal to 0, and x2 plus 3x3 is equal to 5, and x3 is equal to 2, then we say that this is in row echelon form. Because in row 2, the first term is 0. In row 3, the first two terms are 0. So this makes me in this preferred row echelon form. Okay, why does row echelon form matter? So if we look at that example again, we just kind of articulated here. What we get is the ability to back substitute. Because we know x3 is equal to 2, which means that x2 plus 3 times 2 is equal to 5. Means x2 plus 6 is 5, which means x2 is negative 1. And x1 minus 2 times negative 1 plus 3 times 2 is 9. So x1 plus 2 plus 6 is 9. x1 plus 8 is 9. x1 is 1. So we know that the order triple 1, negative 1, 2 is the solution to the system. So that makes things fairly straightforward. Not too bad. So how do we get something into row echelon form? We have a series of what are called row operations. So row operations are things where you can perform on an equation but will not, or a system of equations, but will not change the solution to the system. So one, you can interchange two equations. So you can like take the first equation and make it the third, and make the third equation the first, and nothing will happen. You can multiply an equation by a constant, or you can add a multiple of one equation to another. Okay, so let's give an example of this. Okay, so let's start with the system x1 minus 2x2 plus 3x3 is equal to 9. Negative x1 plus 3x2 is equal to negative 4. And 2x1 minus 5x2 plus 5x3 is equal to 17. Okay, so the first row is fine the way it is. The second row, we want this term to be a 0. So what we do is if I add these together, I'm going to get a 0. So I add equation 1 to equation 2, and I substitute that in for equation 2. So we're going to leave equation 1 alone. And then we're going to start adding these two. That plus that is 0. 2x2 plus 3x2 comes out as x2. 3x3 plus 0 is just 3x3. And 9 plus -4 is 5. Now we've done nothing to the third equation, so it stays exactly as it is. Okay, so now my issue is I have a 0 here, which is what I want. I'm okay with that term being there. This needs to be a 0. So I'm going to multiply again the first equation, this time by -2, and add that to the third equation and substitute it in to where the third equation is. So the first equation does not change. The second equation does not change. And then we multiply the top equation by -2 and add it to the third equation. So that's going to become 0. -4, -2 times -2 is 4, minus 5 is -1x2. Okay, -2 times 3 is -6, plus 5 is going to be -1x3. And then finally, -2 times 9 is -18, plus 17 is -1. Okay, so we're getting close. The issue here now is this term. So in order to make that a 0, we're just going to add the second equation to the third equation, and we're going to substitute that in for the third equation. So first equation stays as x1 minus 2x2 plus 3x3 is equal to 9. The second equation becomes x2 plus 3x3 is equal to 5. And the third equation, so we're going to add these two, gets me a 0. 3 minus 1 is 2x3. 5 minus 1 is 4. So the only thing that I have a problem with here is I want to make that 2 into a 1. So I'm going to multiply the third equation by a half and substitute that in for the third equation. So I leave the first equation alone. x1 minus 2x2 plus 3x3 is 9. x2 plus 3x3 is 5. And finally, x3 is 2. Now, if you look carefully in your notes, you'll find that earlier in the notes, this is the exact equation in row echelon form that we solved earlier by back substitution. So we're ready to do back substitution, and we're going to get again that the solution to this system is 1, -1, 2. So this is a bit of a tedious process of putting it into row echelon form and then back substituting, but it's very organized and efficient. Ultimately, we're going to strip away a whole bunch of the notation here, and we're going to create something that's called Gauss-Jordan elimination, and that, aided with technology, is going to go lightning fast. But right now, there's your introduction to systems of equations.